Well, this is section 6.4, Fundamental Theorem of Calculus. Sounds important, right? And it is very important, thus the name, Fundamental Theorem of Calculus. This, on a side note, is Morro Rock in Morro Bay, California, and it was about 25 or 30 minutes from where I used to live in California, and it's a big rock. Okay, now keep in mind this is not my favorite calculus textbook quote. Okay, I'll be honest, I don't have one. But this is Greg Kelly, the author of these videos or the PowerPoints, his favorite all-time quote from a calculus book. If you were being sent to a desert island and could take only one equation with you, this particular one might well be your choice. And as you can imagine, this is the fundamental theorem of calculus. So here's how it works. If f is continuous on a closed interval ab, then the function, notice the capital F of x, we've got this an integral from a to x, f of t dt, has a derivative at every point in the closed interval from a to b. And on this next part, if you take the derivative of an integral, now keep in mind how we evaluated integrals. We took the antiderivative. So it's like you're doing the derivative of an antiderivative, so you get the function. They undo each other. They're inverse operations, and they undo each other. And that's the idea of the fundamental theorem of calculus. And what makes it really kind of powerful is it links together the idea of derivatives, antiderivatives, integrals. It just kind of links all of that together. So here's how it works and what you have to have in order to use this. You have to be taking the derivative of an integral. That's a must. The derivative has to match the upper limit of integration. So if it's d dt, then there has to be a t at the top. So whatever, those have to match. The lower limit of integration has to be a constant. And then we have our new variable. Notice we're just using, whatever this is here. You're literally plugging it into whatever the function is. So for example, here's the long way. This is not using the fundamental theorem of calculus. This is evaluating the integral using antiderivatives and then taking the derivative of that. So the antiderivative of cosine t would be sine t, and you would evaluate that from, with plug in an x and negative pi and then subtract like we've done. So you'd evaluate that. Sine of negative pi equals 0. So you get the derivative of sine x. They're just carrying the derivative sign down. So the derivative of sine x is cosine x, and that would be your answer. Here's the method, the way using the first fundamental theorem of calculus. We're taking the derivative of an integral. The derivative matches the upper limit of integration. So here's the derivative, matches the upper limit of integration. The lower limit of integration is a constant. Negative pi is a constant. So you plug it in. You don't do any other work, you just plug it in. Looking back at practice, AP exams, the fundamental theorem of calculus, as you can imagine, shows up on the AP calculus test numerous times, both on the multiple choice and in the free response. So you definitely want to recognize it and know how to use it, because it really can simplify problems for you. So here's another example. We're taking the derivative of an integral. The derivative matches the upper limit of integration. They're x's. The lower limit of integration is a constant. We've got a 0 there. So you literally plug in the x and you get 1 over 1 plus x squared. Easy. Now for this one, notice we're doing the derivative of an integral, but it's not just an x. So here the upper limit of integration does not match the derivative. It's not just an x, but all we have to do is include the use of the chain rule. So using, what they did here was that you plug in, because everything else matches, everything else works. So you take the x squared and you plug that in where the t was. You plug in an x squared, and then you just take the derivative of the x squared. This is the chain rule right here. So you end up with cosine x squared times 2x, or you could put the 2x in front. Okay, so on that, again, what you're doing is, because this didn't match exactly, you still plug in the x squared and get cosine x squared, but then because it wasn't just an x, you have to take the derivative of what's inside. Okay, so on this one, we've got the lower limit of integration is not a constant, but the upper limit is. So we need to switch them. And we're going to change the sign of the integral and reverse the limits. So remember, if we've done that already. That's one of the rules for integrals, and so we make use of, so that we get everything in the right place. Now we can just plug in an x because everything else matches up, and it's just a negative instead. So on this example, notice that neither one of them are constants. So we don't have a constant. So there's a trick to these. We can still use our plugging in method. We split the integral into two parts. So typically 0 is used, but it doesn't matter what constant we use. You could go from 2 to x squared and from 2x to 2. It doesn't matter, but 0 is a lot of times what's picked. But notice, following the rules for adding integrals, if you added these two integrals together from 0 to x squared, from 2x to 0, I probably would have put this on the left-hand side. But then when you add them together, you get the integral from 2x to 2x squared. So, so that's what you do. You just break it up. And then we still have to do a little bit, because notice I don't have a constant at the bottom here. So we just switch that. So change this to a negative, and then switch the order of the limits. Okay, now we're ready to plug in, but don't forget we will have to use the chain rule. So here is what you get. So they just plugged in an x squared where the t was, but then they had to take the derivative of x squared, which was 2x. And then here, plugging in a 2x where the t is, and the derivative of 2x is 2. Okay, so using the chain rule. And then you could just clean that up a little bit to simplify it a little. So notice that was part 1. The fundamental theorem of calculus part 2 just says, and I'm going to skip down here again, these are f has to be continuous on a closed interval, and the antiderivative of f, if f, capital F, is an antiderivative of f on that same closed interval, then we end up with this, where the capital F, remember, is the antiderivative. So you take the antiderivative, plug in the upper limit, plug in the lower limit, and subtract. That is part of the fundamental theorem of calculus, and we have already been doing this, so we already know this. So to evaluate an integral, you take the antiderivatives and you subtract. So I will also be making a video of some examples from our textbook, so you guys will have a few more examples of before you start your assignment.